Hi, I wanted to do some examples of the normal distribution and probability. The normal distribution is very important because we can model data and do predictions and probability and a whole host of different things that we can answer knowing that we can model data to a normal distribution. So if you're familiar with a normal distribution, it's this bell-shaped curve. And then we know that the y-axis equals our relative probabilities. Everything under this curve is going to equal to 1. So the rare events are going to be at the end of this curve. And then the width of this curve is demonstrated by the standard deviation. And this is a standard normal distribution. So the mean is at 0. And that means that the data is going, or values are going to be centered around our mean. And our mean doesn't have to be 0. You know, if we're dealing with real world data, which we're going to look at different examples, your mean could be anything. And the data should be centered around this and have this symmetrical shape. There's a rule that for a normal distribution, about 68% of our data is going to be within one standard deviation of the mean. And then 95% of our data is going to be within 2 standard deviations. And then 99.7 is going to be within 3 standard deviations. So let's get started. So let me zoom back in here. And we're going to look at visualizing the normal distribution in Python. So we're going to use Scipy, Seaborn, and Matplotlib. And then we're going to look at a few ways to model data with this normal distribution using some functions. And then we're going to answer some probability questions also using some functions from the Scipy library. So let's just get started. So what we want to do is start visualizing our data. So here are some examples. We have baby height. Imagine we know the average baby height in inches is 20 and a standard deviation of 0.6. And height is going to follow a normal distribution. And we want to look at the average of an adult is 70 with a standard deviation of 4. So let's generate this. So I'm going to press escape and B. And I'm going to load in these libraries. So I'm going from scipy.stats. I want to use the norm package. So import norm. And then and let me zoom in here a bit so we can see this. So then we just need to import Seaborn and save it as a variable SNS. And I want to import matplotlib.pyplot as PLT. And this is going to help us with our calculations, the Scipy and norm. We're going to import Seaborn to create some visuals, and then Matplotlib is going to help us stylize things. So let's just run this, and we can press Shift and Enter to run that. I'm going to create a few more cells using escape and B. All right, so now once we have this, we can start creating some sample data based on our information. So if we know these 2 elements of a data that follows normal distribution, which is the mean and the standard deviation, we can start modeling that data. From norm, I'm going to use RVS, and I'm going to open that up. And then you can see it says random variates of given type. So what we're going to do is pass it some of our information. So we're going to pass it our mean and our standard deviation. Now we said in our example that the average baby is about 20 inches, and the standard deviation, which we're going to signify with scale, is 0.6. So if I just run that, you can see what it's going to give us. It gives us a random variable that is going to say, okay, well, this is a random height. So we can say, give me more than one. We can say, give us 100. So if I do that, we can see that we are going to generate data that follows our normal distribution, given that our mean is 20 and our standard deviation is 0.6. So we can increase that to 1,000. Now, I'm going to save this as a sample, and I'm going to say, and then equals norm. So we can do the same thing for adults. So I'm going to just, well, let's see what that looks like first. So we said the average is 70 inches with a standard deviation of 4. And just let's not pass in this to see what we generate. 70.4. What if we do a size of 10? And let's see, here would be all our different ones that are going to follow that model of standard deviation. So I'm going to do 1,000 for that. And I'm going to call this adult. So the next step would be visualizing this. And we can visualize our distributions with a histogram. We can use a KDE plot, and then we can use a disk plot that is native to Seaborn. So let's just use Seaborn, which we saved as a variable SNS, to give us a histogram, a baby sample. So if I run this, now we see that this normal distribution, now it's a little jagged because we're using a histogram, but we can look at this as a disk plot, which will give us a different way to look at that. And you can see now we see this bell-shaped curve start to generate. And of course, we can do the same for our adult sample. But now you can see when we were talking about that standard deviation. The shape of this data is the same, but we can see that the shape of the baby weight, the standard deviation is very tight. So there's not a lot of variation in height for babies. They're pretty much the same size, and there's not a lot of extremes. But of course, adult height, you're going to have a wider width because adults can be at all different heights depending on your culture, where you were born, male or female. So that's why the standard deviation is going to help us to see the width of the curve. Also, look at another example. Let's imagine that I have a business, and my business, we produce batteries. I'm going to put some document. Our battery life follows a normal distribution and has a mean of 6 and a standard deviation of 1.5. I'm going to turn this into some markdown and new example. All right, and then I am going to just, now we have this new example. So we can easily do the same thing. We can just go here, we can copy our data here, get the norm RVS, and if this is our real world data, we can say, okay, what is our mean? Our mean is 6 and our standard deviation is 1.5. We can wrap this in a KDE plot. So now we see that. We can stylize this a little bit. We can fill it and say true. we can do a few things here. Now that we have Matplotlib in, maybe what we want to do is I'm going to take this information and I'm going to save this as battery sample. And I'm going to, and how about we plot the mean? So the battery sample here, and let's get the mean. And I'm just going to use the mean here. So now that I have this, I can actually plot this plt.axvline, because plt was our Matplotlib variable. So I'm going to say, please pass me that. And let's just put our mean there, our bat mean. plt.vline. What am I doing wrong? Oh, a little misspelling there. Bat mean two ends. There we go. So now we have this line here that signifies where we should have our mean. And what if we wanted to see if the rule equals, like within standard deviations, we have 68% of our data. So what we can do is we can take this bat mean and remove mean and put our standard deviation function. We can call this bat std. Okay, so now we want to see one standard deviation before and one standard deviation after. So I can copy this and say, okay, we want to see one standard deviation here, std, and then we want to see one standard deviation behind. So we subtract it from the mean. And maybe we can stylize this. We can say the line style we'll put dashes. And how about we also change the color? I don't know, we can change the color to black. We run that, and now you can see that this is the information we have there. So, and also we should also make sure we check to see what that standard deviation is. So, but see if it follows what we produced here. Of course it should, but I'm just going to show you. So I run that and I get 1.55. So this is a way to see our data model into a normal distribution. You can also use some different functions to see where our data lies. Okay, so we know this interval here is 68% of our data. Let me just zoom out a little bit. So if I is here and I press escape and B to create a new cell, I can use a norm.interval to see what is the interval here. What percent of our data falls within these two intervals. What I need to do is give it the information that I want. We want to know what is 0.68 or 68%, and then we want to know that we know that our mean is, for our battery, is 6, and our standard deviation is 1.5. And let me just create some more cells. All right, so if we run this, I'm going to zoom back in for you. So let's run that. And now you can see that that 68% is going to be between 4.5, which is here, and 7.9. So you can already see how we can use this to model some of our data. So let's talk about using this to predict some probabilities. So let's go down here. So let's look at probability with the normal distribution. Let's imagine that we are going to use the assumption that most adults are around 70 inches, let's say in the United States, and with a standard deviation of 4. So let's just recreate that very quickly. We know we can use SNS KDE plot. We can pass in our adult sample, and then we can look at this curve. We want to know what's the probability of someone being, well, let's say what's the probability. So now that we have this curve, and I'm going to zoom out. So I want to know the percentage of adults that are under, let's say, 75 inches. So we can still use our norm. And now what we want to do is see the area under the curve. So in example, we have 75 here. A little bit off, but you get what I mean. And then we want to know the area under this curve. So all of this, because we know that the probability will equal the area under the curve. So if we have 75, it should be very close to, if we go back up, so we know if we have we go back up here. So if we want to understand what percentage of our population is under 74 or 75, what we're going to be doing from here onwards. So that means everything we should be able to do is add up these different probabilities. It's going to be around probably 87 or 89, 80, around that area. So if we go back down to our example and we say, okay, we want to know what the probability of being 74 or 75 or below, we can use the cumulative distribution function. So I'm going to do norm.cdf, and then you can see what we have there, given a random variable. And we're going to use 75, and then we're going to give it our mean of 70 at loc, and then we're going to give it our standard deviation, which is our scale, equals 4, and then we'll get a probability. So you can see it's around 89%. So what if you wanted to know how many were above 75? Of course, we know all of the area under this curve equals 1, so we could just subtract 1, or we could use a survival function, which is SF, and pass in the same information here and get the same information, which is 10%. So how about LeBron James? He's a very tall individual. So what is the probability of someone being taller than LeBron James? If we know that LeBron James is 82 inches, and we have a model of that says we have a normally distributed population with a height around 70 inches, and maybe this is in America probably, because 70 inches is probably a little tall for everyone. And we have a standard deviation of 4. What's the probability of someone being, LeBron James height or taller? So what we do is we would change this particular value to 82. And then we can see the probability is very, very, very low. And now if we wanted to know what's the probability of someone being between two of these, what we would do is, so we can take our example of our battery, which we have here. So I'm going to take this information here, come back down, and I want to, instead of using, what if we wanted to say we wanted to know what's the probability of being between 4 and 8 hours, is we could easily take our CDF. So we have a norm.cdf, and we know we want everything below 4. So 4, we know our battery life mean is 6, and then we know the standard deviation is, we can just pass in that for our scale, and we can say this is below 4, and then we can say this is between 8 hours, 4 and 8 hours. And then all we would have to do is subtract the two. So let's print 8 minus 4, and that should give us our answer. So we can see that's going to be 83% going to be between 4 and 8 hours. And that's similar to the interval we had there. Okay, that's just a quick and easy way to do probability. Let me know if you're interested in having a few more of these. It would be very interesting to continue on these with different models like the Poisson or the binomial distribution. I hope that helped. Thank you.